Hi everyone, my name is Mykola Lukianov and I'm a PhD student at Gdańsk University of Technology and an early-stage researcher in the Smart GSOOM project. Within this relatively large group of researchers, my task is to study bidirectional EV charging possibilities that will be relevant in the future. Specifically, I'm working on a multi-terminal EV charger powered by a low-voltage DC traction grid. So why this research is relevant? As you may know, with millions of EVs being added to global roads annually, the need for efficient and economically viable charging infrastructure is becoming increasingly critical.
See behind me, there are still a ton of Tesla owners who are waiting to recharge their cars, and those lines only keep growing.
So this research focuses on one potential solution, a multi-terminal charging station based on a multi-active bridge converter. Compared to independent connections, where each EV is connected using an individual converter, let's say dual-active bridge, a multiport connection requires fewer components, making it more cost-effective. This approach becomes even more advantageous when such a multiport charger is integrated with existing low-voltage DC traction grid, like those used for trams and trolleybuses. This integration leverages existing infrastructure such as substation transformers, rectifiers, and other auxiliary equipment shared between EVs and traction transport, further reducing the installation costs of EV charging station. The system also includes a storage battery that is used for traction transport, braking energy recuperation, and as a buffer battery for EV charging. So far, detailed simulation of such a converter with 3 EV charging ports have been conducted. Simulations were conducted using Plex software for 3 EV charging ports. However, the number of connected EVs can be increased depending on the needs. The studied converter power is 250 kW for storage battery charging and 50 kW for each EV charging port. Since the converter is powered by an existing traction infrastructure that was not originally designed to operate with both trams and EV chargers, it should operate with a smart charging algorithm to avoid grid overloads. Thus, the high-level system control algorithm creates reference currents and voltages for the storage battery and EV charging, while the low-level control system ensures that the currents and voltages in the system are maintained at their reference values. It's important to note that in a studied converter, power can flow independently between ports, allowing for any possible power flow direction and enable vehicle-to-grid operation. Duty cycle control was used to manage the storage battery charging, while dual phase shift modulation was applied for EV charging, which, in comparison to single phase shift, helped reduce the RMS currents in the transformers during voltage mismatch between the storage battery and EVs. To verify operation of the converter and its control, work is underway on a 20 kW converter prototype based in the lab of Gdańsk University of Technology. The hardware is partially ready and work on the control board and software is ongoing. Thanks to the IEEE Industrial Electronics Society for the opportunity to participate in a Young Professionals and Student Assistance Program.